Hello everyone. So today we will talk about the lithographies and the wet cleanings for the semiconductor process. So the cover here is the process for the lithographies, which we'll talk in the detail later. So before we start these videos, uh, this series of the tutorials will cover semiconductors process, but it's the fundamental ones. And the reason for me to build up this video is trying to help those major wasn't in electrical engineering, but they are interested in working for a semiconductor industry, such as you're major in chemistry, you never learn about the semiconductor process, but you can see lots of engineer was major in chemistry who work as a process engineer in the foundries. So this video was one to help those who want to have the interview or is having the interview to have more understanding for the semiconductor process. So this will be covered cleanings, lithographies, depositions, or etchings. Before starting off the details, we will have one page for the difference process. So for this video will be photolithography and the wet cleanings. So if you are really in rush or you only have an hours before the interview, you can look into only the one page part, which is the most important part for that process. So for the wet cleanings one page, we will know that we want to do the cleanings of the wafer before we start doing the process or after doing the process to remove any impurities. So for wet cleanings, we might use ammonia with peroxide to remove the organic of the surface, or we can use hydrochloride with peroxide to remove metals and ions. Also, on the process, they use a lot of piranha solutions, which is sulfuric acid with peroxide, and this will be really corrosive, which can remove both metal and organic. However, you will film really thin oxide layers, and it can be removed by the HF. So on the process, we don't actually use only one of them. So probably we'll first use piranha solutions, then we use maybe RCA1, then we use with HF, then we do with UPW. But it really depends. So we will have the split tables. We'll have different combinations of different situations and conditions to see which works best for remove all of the impurities. So if we can see over here, here is the wafers, and mostly it will be on the spinning code, so the wafer will be spinning, and you can start spraying the different chemical onto it. So probably you will do that. There will be two spray. So maybe here will be hydrochloride, and here you will spray that peroxide. And the reasons we want to remove all the organic or the metal is that impurity might cause a defect on the wafers. What does that mean? So here is a example for the lithography, which we will talk in details later. So if you're not really familiar with other process, we will talk in the further materials, but this is only for one page, so I will combine all of the most important part. So here's a mask, here's a oxide, here's a PR, and here's a substrate. So after you do the depositions, you will see, so this is a positive PR. So after that, we will use a developer to dissolve it. So here will be after the developers, and you would expect that this will be clean. However, if the developers, there might be some defect on that. Maybe impurities like metal, it will be on that if your developer wasn't clean enough. Then after that, if you do etchings, the dry etch, in the ideal situation, here this part will be etched away. But if there's an impurity over here, then it will only etch here and here and here, but not the impurity part. So this part might be etched away, and this part might be, but this part will not be able to etch away because there's an impurity on it. And here's another example, which again is lithography. If you got one impurity, maybe metals or mostly particles on the PR, and then you exposure the light, and here it should be negative PR, then you will see here will be a defect on the wafers. So we want to avoid the defect to increase our yield. That's why we might need to do the wet cleanings. So for next page, we'll talk about lithography. So this is also the one page for lithography. If you are really in rush, you can just look through one page. So lithography will have several steps. First is the cleaning substrate. Over here, so we want to promote the adhesions for the wafers. Then we do the dehydration back to dry the clean substrate to promote adhesions for the photoresist. Because we know that photoresist, which we call PR, it's organic. So if there have some moisture on it, it will be hard to adhesions onto the wafers. The next step is we deposit the PR. So in here, they might use some maybe chemicals like HMDS. So since like on the silicon wafer, there will be like, let me draw out. Silicon wafer, there might be also like, there will have SiO2, which is hydrophilic. But for the PR, as we say, it's organic, which is hydrophobic. So if you apply HMDS over here, it will have a methyl group to combine with SiO2, which make it hydrophobic. It will have better adhesions for photoresist. And photoresist, normally we use spinning coat. So here's spin coat, and we put wafer and the spinning is really similar to a wet cleaning. I would say it was the same. Then you spray the PR. And after that, we do a soft back to remove a solvent to set the resist. Then we do an exposure. So on the right hand side, you can see here's a PR. Then here's a substrate. So after you deposit the PR, it should look like this. Then we will have a mask. Then we do an exposure, probably UV. So after exposure, this part will have chemical reaction with a UV. And it really depends. If it's positive, then it will dissolve with the wet chemicals. If it is negative, you will see a cross-linking, which make it more insoluble compared to the chemicals. Then you will do a post exposure back to enhance the chemical reactions and make this stabilize for the lantern image. Then we do a develop, which we use white chemicals to rinse it away as a positive resist, or rinse it away the other part which is not exposed, which is our negative resist. Then we rinse it with water, then we dry it. After that, we'll do a decom. And the reason we do a decom is just as we mentioned, here might be have the defect. And if we do an etching for the next step, here will cause some defect. Then we do a hard back to toughen the resist. As we know that there's a high possibility we'll do an etching after a litho step. If we do an etchings, it will hurt the PR. So as we can see here, imagine this is a PR. And we want to etch the place over here. And first is the decom. We want to remove this kind of impurity, so it might not cause a defect. Second, hard back. If we don't do a hard back and the etching is too strong, then this part and this part may be destroyed. Then you etch more, which you don't want it. It might cause an issue. Then after using the resist, which probably we use etchings, then we strip out the resist mostly with HF or the Perhana solutions to remove the photoresist. And for the exposure, there might be some important parameters. First is NA. So what is NA? So this is a lens, this is a mask, and we will have UV light to head through the mask, then it will be focused by the lens on the specific area of the die. And the NA is how much the die can be connected by this lens. So if we increase the angle over here, NA will become higher. And what is important for the lithography? Because resolution was related to NA. So in here we can see NA is over here. If we increase the NA, actually will decrease the resolutions. And here's another concept, which is the depth of focus, and which is defined as the image range over the wafers for the image that can be sufficiently well resolved. So if this is really though mean that this process will be really hard, since there's not too much range for you for the image to be resolved. As we can see, if this also increase, the depth of focus will decrease. But also we want the resolution as low as small as possible so we can separate the object. However, if we increase over this part, the depth of focus decrease, meaning that like the range which is acceptable becomes lower for the image to be resolved. So there will be a trade-off between the resolutions and the depth of focus. So that's for the one page for the cleanings and the lithographies. And then we will go through detail one by one. What does that mean? First is a lithography. So as we said, for the lithography, first we'll got substrate PR, then you deposit a substrate wafer, Then you deposit a PR onto it. Then you will use a mask, then you use UV light to hit it. So it depends on this is an exposure area, right? So it depends on it is positive resist or negative resist. So you use what chemicals to do a develop. If it's a positive one, the trend will be cut for the polymers or for the chemicals. Then after that, it becomes weakened, so the developer might be dissolved and resist a wet. If it is a negative PR, then probably it can be cross-linking after the UV light exposure, which make it insoluble and even increase the molecular weight. So when you use chemical, you are unable to dissolve this part, but the other part might be dissolved. This is the two different resist for the lithography. But why? Why we want to do this process? Here's an example. So in here, probably this is a part we want to etch. So what we do, we put on the PR. So probably original PR looks like this. Then use a mask. You exposure it. In here is a positive resist. So after developer, here will be empty, and here will be empty. It will look like this. Then you can do a dry etching. Probably you will use a dry plasma to do etching. So this place will be etched away. And this is why we want to use a lithography process. So we'll go through step by step for the lithography first. So first is cleaning the substrate to promote the adhesions. So for cleanings, the wafers, why? Why do we want to clean the wafers? First, if there's issues for the contaminations, it will affect the mobile ions in oxide. So if there's a mobile ion in the oxide, it will change the electrical field and voltage at the silicon surface, which will affect the MOSFET threshold voltage. And if there's an impurity in the silicon, it will impact semiconductor carrier concentrations and distributions. Also, if there's a particle on the surface, it will create numerous problems during the photolithography, and we'll talk about later. Also, probably there will be unintentional films between layers, which cause the open or the short circuit between the layers. Example. So in here, we can see here's a lithography. And after we do exposure, we do a developer to develop the PR. And if here have the impurities, as we can see here, that says your developer, mostly we will use TMA to do that. If it was include some particle in the TMA, probably here will be a particle, here will be a particles. And after you do etchings, this part can be etched away, this part can, and this part can, but not this part. But originally, you want to etch the whole part, right? So here's the defect. And here's another example. Particle over here, you do a photoresist, you do a photolithography, and UV light export it. Then after develop, here might be the negative photoresist. You will see this place was exposed, so there's a defect over here. In general, we will use three kinds of ways to clean the wafers. First is wet cleanings, which we submerge the wafer in the acid in the bath. Second will be dry etch. Mostly we use plasma to do etching, and mechanical, which we use ultrasonic to do the cleanings. For wet cleanings, we can use RCA1, which is ammonia with peroxide to remove organic, or hydrochloride with peroxide to remove metal and ions, or perhana solutions, which is sulfuric acid with peroxide to remove both metal and organic. So here might be a spinning coat, and here's your wafers. Then you have two spray. Here might be a sprayed in sulfuric acid, and here might be spraying peroxide. And after using the perhana, there might cause a thin film over here, and you can use HF to remove it. So in the process, normally we won't use just one kind of chemical to do a wet cleaning. We might use perhana, then HF, then maybe RCA1, then UPW. So we will try different combinations and do split tables to see which works the best. Then we probably will go to use that process to do the cleanings. For dry etchings, first we might remove the air in the vacuum system. Then we put a mixture of a gas, then we inject RF energy to form the plasma. So if this is a PR, and here is the one you want to etch, and here's the wafers. The plasma will be over here, then it will shoot the plasma on it to etch away this part. And it can be used to remove polymer residue and metals. Oh, sorry, this is etching, but probably it's the same idea, but in here we will just do cleanings, not the etchings, my bad. After do the cleanings, we do a dehydration back to remove all the moisture. Then we start doing the deposits of the photoresist. So for photoresist, it was consist of three components: into resins, sensitizers, and solvent. So for resins, we want to provide the mechanical properties. For sensitizers, it is a chemical. This is the most important part, which is the photoactive compounds, which will interact with our UV light. So the PR will change its chemical properties. Then solvent is just solvent. So for the deposit of the PR, our goal is to have a uniform thickness, controllable thickness, and consistent thickness. So in here, we might have a spinning coat, and we put a wafer on it to spin the wafers. Then we'll spread the PR onto the wafers. And how do we know how is the thickness for we to deposit on the wafers? Here's the equations. So the thickness is related to the viscosity for the PR. So if it is high viscosity, you will expect the wafers, the PR will be really thick. And for the velocity, if you're spinning faster, the lower for the film thickness. also the radius of the spinning plate. So if you increase the radius, it will reduce the thickness. So as we can see here, if the spinning speed increase, we will reduce the thickness a lot. And in later we will talk about thickness. It will affect the resolutions. So in general, we want the lowest thickness as possible since it will get the best resolutions. KLA reflectometrics. This is one of the tools we use in our lab to measure the thickness. So it will incident light from the bottom and the top of the probably the material or the wafers, and the reflected intensity will vary with the wavelength, the thickness, and the refractive index, and you will use algorithms to determine the film thickness. So when you're doing the deposits of a PR, you might encounter some issues. First, there might be uncoated area, and mostly it was because insufficient dispense volume. And air bubble, probably there's a bubble in your solvent in your PR center circle. It's because the spin chuck isn't in the proper size. Comets, dragonflares, there will have different reasons, including fluid velocity too high, spin ball exhaust rate is too high, or the spin bit too high. Pinholes mostly was because of their air bubbles. Swirl patterns, it should be the spin ball exhaust rate is too high to cause this issue. So different issue will have because of different reasons for the spinning process. So that's back to the PR. As we know, PR have two types, positive and negative. So here's an example of positive PR. After exposure to the light, this single bond will be cut and it will be weakened. So this is a suspicions for the chemicals. And for negative PR, after it exposed, it will increase the molecular weight or make it insolubles. So after you do a develop, only the place that doesn't be exposure will be washed away. And that's for a negative PR. And there's several challenges for PR. So for positive resist, first it is poor adhesions for the positive resist to the silica. Because we know silica, the surface will be silicon oxide, which is hydrophilic. But your chemical PR is organic, which is hydrophobic. So we will apply something like HMDS, which we have methyl group over here to make it hydrophilic, to make hydrophilic surface become hydrophobic, to have better organic linkings for your PR. So yeah, that's for the positive PR we might encounter as issue. Negative PR, it was swelling during the developer. Then the long narrow line will become wavy. Also, if there's oxygen present during the exposure, it will reduce the cross linkings. Also, most of the most of the PR are organic, which is not really eco-friendly. So for the max shadow, here is the PR, and here probably is a chemical, the film you want to etch away. So if your UV hit over the mask, here's a mask, there will be a light diffractions around the features, causing only this part after develop will be stay. And this is for positive resist. For negative resist, it's the same. Here's a mask, here's a thing you want to develop away. And however, because of the light diffractions, only here will be developer and here will be stay. The next step is the exposure. So for the exposure tool, we know SML is very good at their EUVs. As the years goes, we will reduce our wavelengths for the lithographic. As the wavelength reduce, we can see our feature size of a wafer becomes lower and lower to 5 nanometer, and now we are targeting to N2 and N1 as a TSMC. So for exposure to tools, there might be three different types. First is a contact, and I don't really see before the contact one, but proximity, which mostly was used in the university, projections probably used in some of the industry, and we'll go through it one by one. For a contact, we know the minimum line width, which is over here, the equations. So for this is for the wavelength. So if we decrease the wavelength, we can decrease the minimum line width and get better resolutions. If we decrease the thickness of a PR, so this is why we care about the thickness for PR. If we decrease it, we can also decrease the minimum width and increase the resolutions. So we know the viscosity, velocity, and the size of the spin track will affect the resolutions right now. So here's a mask. Here is a wafer, and here's a photoresist. So they just stick the mask directly contact with the PR, then use a lens to collect the light and hit on the mask. The advantage is it's not really complex and it's really cheap and it's fast, since the mask is the same size with the wafers, so you can expose at once. However, the disadvantage is obvious. You have contact with the wafer, which might cause contaminations, and also there's no magnifications, which the mask will be the same size of a wafer, and it's large and expensive. The other tool will be proximities. So for here, we can see the mask have one space gap between the wafers and between a PR and the mask. So the equation will be changed. Not only a wavelength will affect, the thickness will affect, now the gap will also affect. So we want to reduce the gap, so we can reduce the minimum line width, which increase the resolutions. Advantage, it is fast since it didn't do a magnifications. It exposes all the wafer at once, and it does not contact wafers to avoid the contaminations. However, for a disadvantage, it's obvious compared to a contact one, because there's a gap over here. It will decrease the resolutions. Also, since there's no magnification, so the mask will have the same size as the wafers, which is large and is really expensive. The next one is a projections, which might be used in some of the industry. And over here we got two lens. So the first lens, it was connect the light and hit to the mask. Then you go for a second lens and you do the magnifications to hit on a specific die. So the advantage is it does not contact wafer, and you also do demagnifications, which make the mask become cheaper to make, since we don't need to have be 1-to-1 ratios of a mask and the wafers, and you can do a really good for the resolutions. However, because you do a demagnification, so the dies will expose separately, which take longer to expose the entire wafers, and it is really complex and expensive. So there's some parameters for a projections tool. First is the NA. So we know here's a lens, and here's a UV go through a mask, and you'll be connect and hit on the wafers. And NS means how much light can the lens connect it. And here's the equations. If we increase this degree, we can increase the NA. But what is NA so important? It's because NA will affect our resolutions. If you increase the NA, you will decrease the minimum width, which can increase our resolutions. However, there's a concept called depth of focus. It's a range that can be tolerance for the image will be resolved. So if this value becomes low, what happens is the process will be really difficult, since the acceptable range for a wafer to move up and down is really limited, and it will be hard to focus for the resolutions. So if you increase NA, depth of focus decrease, which will be a challenges for a process, but also you will increase your resolutions. So there will be a trade-off between resolution and the depth of a focus. And for west and method alignment, there will be some misalignment, such as XY displacement or the rotations, which cause the exposure having the issues. Also, thermal run in and run out might be issues for the mask and the wafers alignment. Then we will go through the rest of the process, including post-exposure back, developer, rinse dry, decom hardback, and user resist and strip all the resist. First, we will do a decom. So the reason we do a decom is like after you do a developer the wafers, like here is a PR and here is a wafers. So after you do a developer, here might be some impurities, and we might need to do a decom to remove the impurities. And the post-exposure back is after developers. Why we need to do a post-exposure back? It's because we can thermal redistributions of exposure to avoid the standing wave. And for the developers, we will have different ways to develop it. First, we might be just dip all the wafers into solutions, or we can do a spraying. So here is a spin chuck, and here is the wafers. When it was doing spinning, we can spray the developer, or we can do a dispense developers. And here's the decom again. Sorry, the previous page is for the post-exposure back, which can thermal redistributions of the exposure product. And here's a decom. So again, PR and the wafers. Here might be an impurity. So we want to decom it to remove the impurities to avoid the defect in the futures process. And after we use a resist, such as here is a PR, here's the material we want to etch, and here is the substrate. We might do etchings to remove this part. So you will show like this in ideally. Then we want to remove a PR over here. So we might do wet stripping, such as using sulfuric acid, but mostly we will use sulfuric acid with peroxide to remove it, or do a dry stripping, use an oxygen plasma to do it, and which can avoid the damage for the under layer, which is over here. Over here. Yeah, and I think that's it for the tutorials. And if you have any questions, please just comment below for the videos, and I will try my best to answer. And in the future, we'll talk more about the advanced packagings and also some fundamentals process such as depositions, oxidations, etchings. So this is just a part of the process, and I'll update the rest of the video in the future. Thank you.